everyone. It is my great pleasure to introduce Joe Hellerstein. Joe is a professor at the University of California, Berkeley. He's also one of the leaders in the database community. In fact, Joe already won 2 Test of Time awards for his work on online query processing and query optimization, which is surprising because he doesn't even have gray hair yet, so it seems like prerequisite that's missing. And actually, so his work is not only recognized in academia, but also in industry, and a lot of basically Oracle, IBM, a lot of engines are using basically source code derived from Joe's research. And even today's work, basically today's presentation is going to be about work that follows on from more award-winning work in Joe's group. So Joe's student who did the previous work to this research actually won the ACM Sigmod-based dissertation award. So this should be very interesting. We welcome Joe. Thank you.
Thanks, Magda. Thanks very much for having me. It's been a real treat to be here the last couple of days and talk to many of you. It's a wonderful, wonderful place, and I'm very happy to be here. So it's been a pleasure. So my title of my talk is Declarative Networking, What is Next? And I want to be clear that this is not a question. It's a statement. It's a declarative statement. It's the first of many we'll have in this talk. Okay, so just wanted to get the punctuation right. I do systems work, and you don't do systems work in a vacuum. So I have many collaborators who are responsible for various pieces of this work who are currently at many different institutions, and some of them had been at those institutions all along. So I'm not going to list off all their names. There's a number of students and faculty at Berkeley and colleagues at a bunch of other institutions. So it's been a pleasure and a privilege to work with all these guys. They're just great. Okay, so motivation for the talk. I should warn you, when I'm asked to give a distinguished lecture, the slides get more and more amped up over time to the point where they're slightly ridiculous. So I'm going to apologize. I'm a little over the top here. I wanted to highlight 2 important sources of flux that are going on in the research community right now, particularly in the networking space. So the first thing I want to comment on is the notion that the internet is really changing, all right? And different people think it's changing in an evolutionary way. Other people believe that the internet should be re-architected from scratch. And there's been a bunch of energy around this. There's evidence for both of these directions. I know people here like Tom Anderson were very involved in the Genie proposals going on at NSF to try to get Congress to pay for a redesign of the internet. Wireless sensors and sensor networks have been something of a redesign of networking from scratch. And then on the more evolutionary side, we see work on overlay networks that try to build application-level networking over the internet, and data center design, where again, you're using fairly traditional networking infrastructure to build and evolve things that are beginning to look more and more unusual and strange. So networks really are changing very fast, and that's very exciting. The other trend that's going on at the same time is what I like to call the industrial revolution of data. And so we think about really big data sets. We tend to think about Google these days, or the web in general. And if you think about the web, it's really quite quaint and charming. All that information was typed in by a bunch of nice people. It's sort of like little old British ladies knitting sweaters in the 17th century or something, okay? It's crazy that all this information we have is manufactured by people. And this can't possibly be the trend going forward, that the large volume of data that we deal with is mostly typed by human beings. That's just not going to happen. What we're going to see is that data will mostly be manufactured automatically. It will be stamped out. It will be produced and delivered to you, by machines and by high-speed networks and so on. And so expect to see data coming from places like software systems and hardware sensors and so on in much greater volume than we have nice people typing in nice text. Okay, so these 2 things are happening at the same time. This one, it's quite fabulous that it hasn't already happened. It's just amazing how much text there is on the web. I think we're reaching the limits of it, but it is fascinating. But these 2 things are happening at the same time. And flux is good, right? Change is opportunity. So the big question is, when we have all this change going on in the environment, what we really want to do, right, is we want to take all this loose energy that's floating around there. We want to harness it somehow. And we want to bring it all together and make something new and wonderful. And so the big question I have is not a question at all. It's a statement. In this time of flux, I assert, what can harness and accelerate the energy and innovation? So whatness is the answer to this question. All right? It's what that's going to allow us to harness all this energy. What am I talking about? Yeah. All right. So my assertion is that what is the future? And by which I mean declarative languages. So these are languages in which you say what you want and not how to implement it. Okay, so that's the idea with declarative languages. You should express what you want, not how to do it. And I've been looking at this in the networked context for the last many years with my colleagues. All right, so we're trying to get beyond the implementation of networks via how. So it's very natural when you think about networks that they should be specified declaratively. Things like topologies. Why are those programmed? They should be specified. I want to have a network that has a certain degree and a certain diameter constraint, for example. Routing constraints. I want to make sure my messages between me and the University of Washington don't transit through Stanford. Addressing by content. I want to make sure that I get a message to Steve Gribble, but he's got 17 devices, and I don't want to have to say which one I mean. Right? These are all things where really we want to talk about things at a fairly high level. We just want to specify outcomes. We don't want to specify implementations. We don't want to talk about addressing and that sort of stuff. And I believe, and I'll try to demonstrate today with some background that we've done so far, that once you can do what instead of how, you can also start doing things like who, where, why, and when fairly easily. Because the way you get declarative languages is by building sort of query-style systems. And so you're going to be able to do things like authentication and geolocation and consensus and forensics, building on this much higher level language and framework. And I'll try to show you some of this stuff as we go. And the thing that's going to come together here today is kind of networks and data, and then reasoning, and then perhaps at some point, although I won't promise much yet, actual control and closing of the feedback loop through this higher level way of talking about things. And we're going to get that because we're going to build into what looks like just network plumbing the facilities to be able to do search and query and inference, and then perhaps even things like physical movement. OK, so how did I get to this craziness? Well, here's how I started on this. A bunch of people in my group for a while were looking at querying data over a network. So in 2000, we built a presidential election campaign tracking website where we joined data from the Federal Election Commission with data from Yahoo and data from some crime ratings databases on the web, and produced this mashup, which at that time we didn't know it was called a mashup, that would let you find out, who donated to Bush and who donated to Gore. And we were really sure that campaign contributions were going to be the hot topic in the 2000 election. It didn't quite work out that way. But we were querying data over a network. And we sort of progressed a couple years later. We said, well, that's not that much fun, it turns out. It's pretty easy. So the next thing we want to do is we want to query data by running the query in the network. So let's look at sensor networks. Let's look at peer-to-peer systems where all of the participating nodes in the network are working together to compute queries. And so that was kind of where we were for a while, doing kind of database-y stuff over a network or inside of a network. And then we had this flash, which I'll kind of talk about at length today, that we could actually implement the network using the queries. And that we weren't going to have the queries over the network. We were going to have the network over the queries. The network was going to be built out of queries. And then where we've been going more recently is to look at, OK, but the queries were actually nice when they were queries too. Just implementing a network isn't so much fun. Let's actually run some queries also. So when you have your queries and your networks and some management of uncertainty, this is kind of where we are now. Because the data that you have distributed across lots of nodes in a network tends to be very noisy. And so uncertainty is kind of built in. And so it's the kind of mixture of all these things that I'm most excited about. Today I'm going to try to convince you that the whole thing's plausible. Going forward, I think what's exciting is how all this stuff kind of mixes together and collapses. So a little outline for today. We're going to talk about why, what for a while. We've kind of been doing that, but I'm going to try to do it a little bit better. Motivation. And then say what, which is some language stuff about how you can express actual working things in a declarative language. What, how, some implementation details. What for, I'll actually show you some stuff we implemented. What is next, some things we're working on now, and then hopefully what's it to you at the end. If by then you don't believe me, I'll try one more time. OK. So the usual reasons for doing declarative languages are that they're easier to program. That's where they generally start. And this was true in the database community. They're easier to program and easier to manage. OK, so that's a nice thing. They're great for rapid prototyping. And this is the way you get somebody to swallow this if they don't like it. You say, I don't propose to replace your assembly code. I'm just building a prototyping language. All right? And then once you like the prototype, then you can go and re-implement it in assembly code, because that's the right way to do things. And then what happens is over time, your prototyping language just takes over. And this is what happened with SQL. Okay? Nobody writes database queries by navigating objects on disks anymore. But it's for rapid prototyping and customization. It's easy to get a first cut at something, manipulate it, change it around. it turns out, and I'm going to try to convince you this today, that declarative languages of the forms we use in database are actually fit very well to a lot of distributed tasks. That the basic operations of recursing over a graph, which is very natural in a network, and rendezvous of data, which I call join, is also very natural in a network. And using these two things, you get a lot of distributed tasks implemented very concisely. So there's a good fit between these declarative languages and distributed systems. And there's an examples, and some of this was in Boon-Tao Lu's thesis, of where by declaring things at a higher level, we actually saw connections in network protocols that networking people hadn't really seen. So I'll try to highlight one of those as it comes out. But by saying things at the right level, you learn more. You increase your mental power somehow. Okay. And then where we're going with this is, once you have things declared at a very high level, you have many choices of how to make the how work, how to implement things. So how do you do optimization of these programs? And then I put this in gray. We've got some work on the optimization in terms of state management and rendezvous in a network. And then in gray, I've put the issue, because we haven't worked on it at all, of once you specify things in a nice logical language, you can prove stuff about its properties, its behavior, its correctness. This is attractive, particularly in the networking context when you're trying to push code out to places you don't control so much. How would they trust that your code does things? Well, you can prove stuff about these protocols. It's harder to prove about a C++ program. All right, and you can also implement dynamic checks more easily. So that's kind of the high level. I'd like to dive now to just the end and tell you what we built, okay? And then we'll go back to the middle and explain everything. So what did we pull off using these declarative languages? We started out by implementing textbook routing protocols from the networking literature, which are really very natural queries over graphs. Things like find the shortest paths, okay? And we did this for sort of internet-style protocols and wireless protocols. And our goal was convince networking people that we actually have something interesting to say. And we were able to convince them enough to accept a paper to SIGCOMM. That was our first effort. After that, we decided to build a system. So we built this system called P2 that I'll talk about a lot today, which is an overlay networking system with a declarative language on top. And with that, we implemented some complicated overlay networks, including the chord distributed hash table. And that stuff, the claim to fame is our code is 100x smaller than their code. Okay, and I'll show you a picture of that in a bit. Right around that time, my colleagues at Intel and Rice and Max Planck said, gosh, with all this nice specification, we can talk about why a message arrived at a node. So we can do sort of very nice distributed debugging because we can talk about, we can reason about the consequences of the rules, and we can backtrace why things happened. And we can also do some fancy stuff with like setting distributed watch points. So you can add constraints to the program. If the global network gets into a certain state, stop. All right, so you can set distributed watch points in a very simple way in the language. And they also showed that you can take distributed snapshots using Chandy-Lamport snapshot protocol and express that in just a few lines of our language as well. So you get all these kind of very fancy distributed systems things, very easy to express. And then a crazy thing happened, because we thought this was all about networking. Some grad students at Harvard implemented the Paxos consensus protocol, which is a very complicated beast. Without really talking to us about it much. They just grabbed our system and did it. And they did it in 44 lines. And we looked at that. We said, wow, there's more here than we thought. And we've been, since then, thinking more and more about what crazy stuff we can do with this language other than where we started, which was routing protocols. So that's where we started. Yeah. So we have a system called P2, and you know it's real because it has a stupid logo. So what have we been working on in the last year or two? Well, we wanted to move this into the wireless domain, into sensor networks. So we have another system called Declarative Sensor Networks, or DSN, which takes these language expressions, these specifications, and compiles them down to very, very small programs that run on Berkeley motes, a few K big. And the neat thing about this stuff is that because it's a very open place where you can implement the entire networking stack, we actually did that. We implemented almost the entire networking stack declaratively from the lowest layer of the radio link estimation all the way to application level things like object tracking and all the networking in between. And almost all of those things were a handful of lines of code in our system. So that's a paper we had at Census this year. And then the rest of the stuff is things I didn't do, other people did outside our group. So, well, I should say my student Boon-Tao Lu went to Penn and worked with Martina Badi on using this stuff for security, for being able to talk about who sent you a message and why, and being able to verify that. Folks in Mike Delean's group at Texas have been using P2 to talk about how easy it is to get different replication protocols built with different semantics and configure them. Also in Boon-Tai Liu's group, they've been applying this stuff to mobility. And then the one that surprised me the most recently was Seth Goldstein's group at Carnegie Mellon is proposing to implement modular robotics using P2's language. They basically explicitly said we're using P2. We re-implemented some of it to talk about how to make little atoms move around in a space. And I'll show you a little example of that later in the talk. So it's being used for moving around little atoms recently. In my group, what we're currently working on, I'll talk about it today, is meta-compilation. So how do you build a compiler in the language that we're compiling in this context? And distributed inference. How do you do AI algorithms, machine learning algorithms across the network, and how easy it is to express them in our language. What I won't talk about today, the third thing that currently we're working on actively, is this business of optimizing the programs. It's a little technical for this talk. So that gives you a smorgasbord of things we can do. You don't have any idea what any of this is yet. So let's get going. OK, so now we're going to talk about say what. By showing you a little bit of the language, hopefully you'll get a sense of what I'm talking about. A little context. This is the P2 system architecturally from 10,000 feet. Queries come in a language called overlog, or in a Dataflow graph description, you can think of this as being like a MapReduce program. All right, your choice. But usually we take things in a declarative language, which is overlog, and we compile it down to a Dataflow program. And then we have an execution engine at every node in the network that runs that Dataflow program against some state. There's a clock driving it across the network. And if you like, it's a single program, multiple data parallel execution model, all right, if that's the way you think about these things. Or it's a parallel database, if you like to think about it that way. Or it's MapReduce, if you want to think about it that way. Very distributed. OK. So can I see a show of hands for people who know Datalog? Yeah, OK. So I have to do a tutorial on Datalog. So Datalog is this thing I was forced to learn in graduate school that didn't seem to matter at all. And so let me remind you, if you've seen it, and if you haven't seen it, teach you. Datalog is this language for expressing declarative programs over, usually over data that represents trees or graphs. Here's a tree. It's the family tree of IBM mainframes, which I found on the web. And here is the classic query that you're forced to learn in graduate school. I have a relation called parent with two attributes, x and y. X is a parent of y. And I have a rule that says x is an ancestor of y if x is a parent of y. All right, and that's the base case of induction. And the recursive case is x is an ancestor of z if x is a parent of y and y is an ancestor of z. So you get a picture like this. You know, here's x. X is a parent of y, and y is an ancestor of z. So now I know that x is an ancestor of z. And then at the end, I can ask a query like, find me all the ancestors of s. OK, and that's the classic Datalog example. And I never was sure how you were supposed to pronounce A and C. But ancestor works. So this is really old stuff. It's from the 80s. It sort of bled into the 90s a little bit, and then people gave up because it got really abstruse and theoretical. And then the internet came along, sort of because of the web, and the internet changes everything. So it's all different now. Now we don't have ancestors and descendants. We have links and paths. All right. And here's x and y and z, and all I want to do is find a path. Is there a path from anywhere to s? Totally exactly the same query. OK, names have been changed to protect the innocent. So the point is, it's a graph. You want to know recursive properties of the graph. It's very natural to think about this in terms of Datalog. So let me step you through it, because this isn't quite what we want. This is a query that finds out connectivity facts. It finds out whether there are paths between two nodes. It doesn't tell you actually how to get anywhere. So let's augment it a little bit so we actually get some paths out of it, OK? So we're going to change the program. The things in colors are different. So the first thing we'll do is every link will have a cost, c. And if you have a link from x to y of cost c, you will have a path from x to y of cost c, OK? So those yellow things are cost. And then the other thing I'm going to add is this blue business, which is, so that's cost 2. It's derived. The blue business is going to be the next hop in the network. OK? So what this says is if there is a link from x to y of cost c, there's a path from x to y. And to follow that path, please go to y next. And it's of cost c for the whole path. OK? So y is the next hop along the path. And you can then augment the last rule in our program in a pretty natural way. So we want to compute costs of paths. One way you can compute costs of paths is to sum them. So if I have a path from y to z of cost d, and a link from x to y of cost c, and the path connects up, then the total path cost should be the sum. If you were doing things like bandwidth, it might be the min of the capacity Okay, so you could have a different function than plus there. It's up to you. But that's the cost computation. And the next hop computation is the other bit. We need to do that recursively. So here we go. We know that there's a path from y to z, and the next hop is some node n. And we know there's a link from x to y. We want to get from x to z. The next hop on that path is y. Right? So we're going to go from x to y, and then from y we would go to n, etc. But we're not going to record n there. We're going to record y. It's the next hop. So we now have a protocol that finds paths in the network. So that's good. It's still not really a routing protocol. This finds all paths in the network. Right? So in 3 lines, we've got all paths. But what we really want is best paths, right? Shortest paths. All right, so let's augment our program a little more. We have a link from x to y. We have a link from x to y. We have a path from x to y. This is all what we've seen before. We're going to add a rule. This rule says, if there's a path from x to z of cost c, look at all such paths, give me the one of minimum cost, and record that fact. So there's a path from x to z of cost c, and that's the minimum cost. It's not a path, it's just a cost. And then we combine that back with the actual paths. We say, find me that path from x to z that has the cost equal to the minimum cost. That's the best path. Okay? We now have something that's kind of like shortest paths routing specification. All right? And it's 5 lines long. That's pretty good. If you read a textbook and they have pseudocode for shortest paths, it's also probably about 5 lines long. So not that much better than pseudocode. You can ask a query if you want here. All right, so what have we done? We have a logic for path finding. It sort of assumed there was a database of links floating out there in the cloud, right? That's nice, nice pedagogically maybe, but it's not really actionable. So the question is, does this insight lead you to distributed protocols that actually run on a distributed set of nodes? And how much more do we have to add to this language to actually get something useful? And the answer is almost nothing. And this is the fun part, OK? So that was the primer. Here's the fun part. What I want to do is I want to make this thing send the messages along the links and find me the paths. And so here's how we're going to do it. We're going to say, look, logically, we had this big table of links from to. Physically, what we're going to do is we're going to take that table, we're going to slice it horizontally, and put some of the rows on some nodes and some of the rows on the other nodes. Okay? And that's the way you traditionally take data and partition it around in a network. How will we partition it? This way. We're going to have an address field in every table. One of the columns is going to be of type address. And we'll mark it with an @ Okay? We'll call that the location specifier of the table. And then your data placement is just based on the location specifier. All tuples, all rows where @ equals x are stored at node x. All right, so I'll show you a little example. The cool thing about this is that's all I'm going to need to add to the language, and I'm going to get all the communication, and it's all going to work. So these partition specifiers are going to induce communication. So let's watch this. Here's the link table, and now what I'm saying is links are stored at the source of the link, at the from. All right, so every node has a link table that says who they point to. And that's the usual way things work. Okay, so I'm just saying the way it is. All right, now here's paths. If you know that you have a link from x to y, you should store locally that you have a path from x to y. It's the recursive rule that's interesting. All right, so let's have a look at this. I have a link stored at x that says that y is my neighbor. I have a path stored at y that says from y you can get to z. I want to know that there's a path from x to z. But these two facts are at different nodes. Okay, so let's look at an example. Down here I have a little network. And I've shown how the link table is spread across my 4 nodes in my little network. These are the links between them. A, B, C, and D are in a line. A and B, there's cost 1 link there. B to A, B to C, etc. Right? And you'll notice that because the @ sign's in the first column, A facts are stored at A, B facts are stored at B, and so on. All right, and what I can see so far is the first rule. All right, that the links have. Did I go too fast through this? No, I don't think so. No, we're still good. All right, what I need to do to get that third rule going, so I've got the links and the local paths. I want these transitive paths. Here's the problem. Okay, this fact that there's a link from A to B and this fact that there's a path from B to C or B to D are on separate nodes, and I have to put them together. Right? So I'm going to need to do some communication here to make this happen. All right. So what we're going to do is we're going to get that communication using the traditional data log trick, which is by rewriting the program. Oh, and by the way, the facts have to land back at x. Okay. So here's what we're going to do. We're going to rewrite the program. This is called the localization rewrite, and it's a totally syntactic rule that tells you how to rewrite programs to get this. We're replacing that third rule with two rules. The first rule takes the link table and redistributes it into a relation linkd that's partitioned by the destination instead of the source, all right, which is just communication. We're just sending our link table to our destination. And then we're going to join the link destination table with the path to get the answer and send it back. So you can see those are now at the, what am I doing here? These are actually at the same node. All right, so watch how this works. Everything is now local. So what we've done is we've said send the link, which is at A, to its destination B, right? So we've sent that. That's the execution of that first of the two rules. And now everything's local. A goes to B, B goes to C, right? These are in the same place. We can put them together. And then we can tell node A that A goes to C, right? And when you do this for everybody, now you're going to get linkd distributed. Everybody send their links to their neighbors. And now we can do the full join and get the answers back, OK? So now we can join those together at the same node, send the answers back to the source, all right? And we do that for all the facts, and we get the full link table. So the crazy thing about this is a network protocol called distance vector routing. All right, so this rewrite I did to this program, which made it 4 lines instead of 3, has achieved communication behavior that is a well-known networking protocol called distance vector routing. Distance vector routing is usually described this way. Take your link table, send it to your neighbors. It's called an advertisement. So you send out advertisements, and then people put them together with the paths they know, and they send them back, which is really what we're doing. But we just saw it as a syntactic rewrite of this program. Yeah?
So this all makes sense if it's static. Do you need temporal logic if things are dynamic?
Not unless you want to capture the changes over time. You just need to maintain these derived relations.
Failures. So, I mean, in general, people don't use distance vector because its behavior isn't particularly helpful in real circumstances.
Good. I'm glad you mentioned that, because one of the other things we could have done to the program when we rewrote it was rewrote it so that the paths moved to the links instead of the links moved to the paths. So we could have rewritten it so that instead of already having a link D, we would have had a path D, and the paths would have gone backwards to the links. That's actually dynamic source routing. It's a different networking protocol, compiled from the same declarative statement. All we said was form paths transitively and get them home. And depending on how you compile it, you get an internet protocol or a wireless protocol. Now, which is better when is sort of the optimization question. All right, but we now have the flexibility to choose between these from a single specification and maybe implement it differently in different parts of your network. So in the parts where there's failures a lot, you might compile it one way, and in the parts where it's fairly static, you might compile it another way. All right. I don't want to spend a lot of time on that right now. The point was to show you that in a very simple specification, in a language where there's no command called send, all right, you get messaging and you get traditional protocols. And that interesting observation that in the same statement, using one of 2 different query optimizations, you get a wireless or a wired protocol, is not something the networking community had sort of thought through before. Okay, and it's kind of nice because it really does lead you to say things like, golly, if my network were very heterogeneous, I might want a program compiled differently in different spots. Right? It sort of takes us towards an environment where we stop thinking about the network as being patches of one of k things. We start just optimizing for cost benefit. OK, so that hopefully gives you a flavor of the language. Pretty good. All right, what I want to talk about now is a little bit of how this works. All right, and it works, as I said, by compiling things down to Dataflow. OK, so just to give you a flavor of that, here's a little snippet from our chord implementation, which is a 47-rule program. These are 3 of the rules that do lookups. It's not important that you read them and interpret them right now. I just want you to see them because this is what they get compiled to. They get compiled to a Dataflow program. This Dataflow program has a bunch of different things in it. It's kind of interesting. It has networking stuff around the edges. At the bottom, it's got some tables, which you can think of as just stored database tables, although we keep them in memory for the most part. As I said, around the side, it's got networking stuff. And right now, this is boilerplate, so we slap this around every program. It's got things like congestion control and muxes and demuxes and stuff like that. This is one thing we're not doing right now declaratively in P2, although we are in the SensorNet stuff. Okay? And then in the middle of it, it's got stuff that looks like query processing, right? It's got joins and selections and aggregations and stuff like that. So the system was modeled very much, the runtime, on a network router toolkit called Click that came out of MIT. It's kind of a generalization of Click at this level, except it's got database stuff in the middle of it. Okay. If you really like, you can write these Dataflow programs. Okay, so some people we thought wouldn't like declarative languages. They would want to write MapReduce programs. We have 0 users for this language as of now. Everybody's been using Overlog. However, because we compile Overlog to this, retargeting our optimizer is very easy, which has been nice. Okay, because the next thing we're going to do is try to take our runtime and just throw it away and use the optimizer and retarget it at lots of platforms. All right, so it has been useful to have this Dataflow language in between, but as of now, nobody seems to like to program Dataflow. This is pretty much the Click language with some bells and whistles. Okay. So I want to talk a bit about some real programs. We talked about this sort of cutesy routing protocol, right? But I want to show you some real programs, very complicated programs. And we'll start with one from the SensorNet domain. So this is a program called Trickle, or a protocol called Trickle. It's a code dissemination and version coherency protocol for SensorNets. So the problem statement is you have some multiple versions of a program that you want to distribute in a wireless sensor network. You want to make sure all the nodes have the same version of the program. And so it's a gossip protocol to gossip out the code and make sure everybody agrees with their neighbors on the version. Okay? And it tries to do things like not have everybody talk at the same time, because then you get collisions and you get failure. So there's wireless stuff built into it for stepping back and giving people room to talk. And this is the pseudocode from the paper. Okay? It's a 6-line table of events and actions. And on the right-hand side is our implementation. This runs. Okay? And these are the correspondences of our code to the pseudocode. All right, and a bunch of the pseudocode is a comment, which is a copy of the original, okay, from the paper. So it's almost 1 rule per line of the pseudocode. And the point we wanted to make here was that we're not just saying this is natural. It really seems in lots of cases to be the way that the people who came up with the idea for the protocol were thinking about it fits in our language. Okay? So without reading it too carefully, I just want to give you some runtime stuff. So lines of code, the original implementation from Phil Levis when he did it in a C-based language for the motes was 560 lines of NESC. In our language, it's 13 rules. Okay, and you just saw them. That's 25 lines, the way we formatted it. And then there's some performance graphs of these 2 protocols running on a set of nodes in different configurations. And the question is, how long did it take the code to get disseminated properly? And you can see the lines are almost exactly the same. So performance-wise, this stuff looks about the same. The only real question then is it feasible to compile our program down to something runnable on the motes? And here the numbers aren't that bad either. So the native code is 12K. Our code is roughly 24K. Except that we have this choice of whether we compile things into the code or into data, actually. We play games with that depending on the platform. Some of the SensorNets have more data memory than code memory or not. So we get to play with that. But something like 28K versus 13K. We pay a little overhead for our runtime, okay? Because we have this sort of fixed cost of deploying the Dataflow runtime. But the numbers are really, really small. Let me give you another example in the internet space. So this is P2. That's the internet version of this stuff. We decided to take this problem on because we wanted to build something that wasn't a toy. We wanted to build something complicated. And the most complicated network that people were really into at the time was distributed hash table. So if you weren't following the buzz 4 years ago, distributed hash tables were essentially content-based routing schemes where you could say, I want to send this message to the node responsible for value k. And that might change over time, and so that's fine. That gives you some indirection. So you might have your mail proxied at one machine, and then it might go to another machine. You are k. OK, k may move around on the network, and I just want to send a message to k. All right, so they conceptualize this as it's like a hash table in the sky. I want to do a key insertion of key value k, and I want you to be able to retrieve from key value k. All right, as the network is changing and storage locations are changing. So it's a pretty cool thing, and it's a very useful building block for lots of stuff. And most recently, I guess, Amazon has this paper called Dynamo about how they use it in their cluster. So distributed hash tables have been useful in the distributed context and in the cluster context. They're really neat. And the Cord paper is beautiful. It's just a beautiful piece of computer science. So they have this wonderful implementation at MIT we tried to emulate it as best we could in our language. So we tried to do a pretty high function implementation, not sort of a simple prototype, but something pretty close to the real thing. And if you know Chord, we tried to throw in all the bells and whistles from the paper. So multiple successors, the stabilization logic, optimize the finger maintenance, do failure detection. Tom was asking about failure detection. In our language, there's 48 rules. Okay? Here they are. All right, there will be a quiz. I'm not showing you this because I expect you to read it, obviously. I'm showing you this because I want to convince you that you could take it to the atrium with a cup of coffee and read it over. Okay? So I want to give you a sense of kind of when you hold the program in your hand, how complicated does it look? That's how complicated it looks, one piece of paper. All right? MIT Chord is 10,000 lines of C++. You don't take 10,000 lines of C++ to the atrium and read it over with a cup of coffee. Okay, so when I'm talking about code sizes, I wanted to give you kind of a gut sense of the qualitative difference you get out of declaring things at a very high level. So does it perform? Yeah, it performs pretty good. So we ran it on 100 Emulab nodes, simulating 500 computers. This first graph tells you that the code's not broken, that it's behaving the way the big O performance expectations of Chord should. You should have logarithmic lookup count. The latencies are OK for a distributed context. It's very bandwidth efficient. We were very gentle with our stabilization and things like that. The hard thing with these peer-to-peer protocols is how do they behave as nodes come and go from the network, as there are failures, or as people join the network in the peer-to-peer context. And here, the C++ code from MIT is better. Okay? So they have this amazing thing where if the average life of a node is 47 minutes on the network, 99.9% of the time, all the nodes agree on the location of some key k. All right, so it's almost completely consistent what everybody's worldview of this thing is. We don't do quite that well. All right, so here's the comparable number. We get 96% consistency. And you know, this is the price you pay for using a prototyping language, okay? Could we tune this up? Yeah, you bet. I'm sure we could hit that 99.9% number. Do we want to? No, we got much better things to do, all right? Which we assume so does everybody else in the world implementing almost everything. All right. So depending on my audience, I tell different versions of that story. Actually, I gave this talk at MIT, and I gave both versions. But they were pretty nice. They've been gentle. So here's another program I'm going to show that I didn't write. This is from this MELD paper from Carnegie Mellon. So Seth Goldstein has this project on claytronics, they call it, or dynamic physical rendering. And the idea is you'd have little objects, and they would sort of move around. And in aggregate, they would behave like matter. Okay? And so you have millions of these little atoms, and they move around, and you want to program them to do stuff together. And right now, as far as I can tell, they have these giant beach balls in a big garage. That's their atoms. And so they have this paper about how they want to, how the hell do you program these autonomous little guys? They have to communicate with each other. They have to make decisions together, but they're autonomous. And they said, well, we really like that P2 language. It's the only thing we've seen recently that looks like distributed autonomous computing. And so they went ahead and they wrote a paper saying, we're going to implement a language called MELD to move our robots around. And this is their program for getting the little chunk of ball bearings to go somewhere. So you have a destination, and this is the program that gets the ball bearings to move en masse to the destination. So the evil Terminator 2 goo follows you down. And it's a 3-line program in a P2-like language. And it's very simple. It just says if you have a few nodes and one of them is further away from the destination than another, then it should move around it. Okay? So that C is further away from the destination, so it moves around. And that's what this program says. And all the nodes are programmed with this, and they move to the destination en masse. So it's pretty cute. Okay. So the next topic I want to talk about, the next topics are what we're working on now. This was all kind of background, honestly. And the reason for the title of the talk is we've hit a phase in this work where we are very convinced, and many of our colleagues and antagonists are convinced that this is plausible. All right, that you can actually build stuff in these languages. Whether people will like the language or not is a very different conversation, but it's plausible.
Comment on how you might embed this in some larger system. So to take a concrete example, the BitTorrent client is a million lines of code or something like that, but the P2 part of that would be 10 lines.
Right.
So
that's a really good question. I see this kind of, well, so more generally, I should be very clear. This is not a Turing-complete language. Okay, it's not intended to be. It's not going to replace all of your program. And so Tom's question is very relevant, which is how do you combine this with more expressive power to get behaviors like that you wouldn't want to write this way. I'm not exactly sure. We haven't bothered proposing anything at all, quite honestly, so we haven't even worried about it. There are good examples, like the C Omega work from Microsoft is an example of embedding a set language inside a procedural language, and their commercial version of that, which is Link with a Q. There's database stuff like JDBC, which is kind of yucky. It's a really good question. I'm not even going to try to answer it, but I did want to expand on why it's a good question for a minute. Yeah. There's surprisingly much you can do with this, though, because so data log is p time, OK? People tend to write polynomial time programs, especially when they're communicating over a network. So from an expressive power perspective, there's actually a lot of useful things you can say in this language, and there's not that many useful things you can't say from a theoretical point of view. All right, so for instance, you talk about BitTorrent clients. You can imagine that the user interface deals with whatever clicks and whatnot. Actually, this is pretty natural for talking about event-driven user interfaces. And I don't think I'm the first person to propose rule languages for that. I seem to remember interviewing for graduate school at the University of Washington and talking to somebody here about rule languages for user interface layout. So, there's lots of things you can say in these kind of languages. I don't have a strong opinion about which are the best ones to choose. OK, but the upshot with this is I hope you believe, I believe anyway, that all this stuff is plausible. And then the question is, could you please stop writing papers showing that it's plausible and get on with something interesting? And that's kind of what we're trying to do now. We've gotten ourselves over the hurdle of could you have a language this small? So here's one of the first things that I've wanted to do, and we're finally doing with this stuff. There was this just knockout work that Carlos Gestrin and Mark Paskin did at Intel when I was the director. I inherited those guys on doing inference algorithms from the machine learning literature in a distributed sensor network where nodes come and go. So you've got all these noisy information coming from these sensors, and you want the nodes together to agree on the distributions of likelihood of things you really care about, not like what does the temperature sensor say, but is there a fire? Okay? And they had this really great paper on how to do that. They sort of implemented it. It was really hard to implement, okay, especially in these little moats. And I thought, I bet those algorithms that they're using for inference would be very easy to express in our language, because really what they are is they're transitive closures. And we just did transitive closures, shortest paths, right? So it also fits into my context, right? So I've got the industrial revolution in data. There's data. It's on networks. The data's noisy, typically. And the challenge is I want real-time knowledge of what's going on, despite the uncertainty, and despite the fact that maybe I can't even go get all the data, right? It's expensive to go get all the data out there. I only want to get some of it. There's tons of applications like this. Internet security is one that we're real interested in, and working with Nick Feimster at Georgia Tech on using it for that. But Carlos has been doing things on controlling a building, a big skyscraper. It's blinds, it's air conditioning. Disaster response, guiding people out of buildings during a fire is another one Carlos does. Robotics, obviously, I've mentioned. And really, anybody running a distributed query engine should be worried about uncertainty, because the data is no good. Okay? When you're talking about data at scale, it's going to be noisy. So I've been completely perverted by these AI guys. So if you've never seen a graphical model, which probably everybody here has, but if you haven't, real quickly, the representation is you've got a bunch of nodes and edges, and you pass messages between them. So that should sound kind of familiar from the first part of the talk. But the nodes here are not computers, and the edges are not network links. The nodes are random variables, and the edges are messages being passed between them in a logical sense. Okay? They're basically they're little matrices being passed back and forth and marginalized and summed and stuff, producted. And so what's going on here is that some of these nodes will have data, and some of them won't. And you pass messages from the nodes with data to the nodes that don't have data back and forth in a particular pattern. Okay? And at the end of it, you've got probability distributions for the nodes that you didn't sample, that you don't have data for. And so belief propagation, which is the sort of the baseline of how you implement these algorithms, is cast as a message passing algorithm in the AI literature, even though there's no network and there's no messages from a system sense. Now what we want to do is we actually want to do this across a network using different computers sending real messages. And so Paskin and Gestrin had this lovely picture where they show that it's kind of graphs upon graphs. So you have some physical network at the bottom. Think of that as the internet. And you have some logical network. Think of that as an overlay like Chord or something like that you've implemented in software. And above that, you've got that graph I showed on the previous slide, which is the reasoning graph. And you want to pass messages on the reasoning graph that translate into overlay messages, which then translate into TCP packets on this guy. And you get to design the overlay, and you get to design the graphical model. Okay? So there's an opportunity here to make these two layers easier to say in my language, and then possibly to co-optimize them together. Okay, to kind of come up with a good version of each of those two graphs that's sensitive to the total cost of the system and the total benefit of the system. All right, first thing, even the fancy belief propagation algorithms are easy to say in our language. All right, so the junction tree algorithm, which is the exact algorithm for inference, using the robustness stuff that Paskin and Gestrin introduced for nodes failing and so on, is 22 rules in our language. That's only 10 times smaller than Paskin's code, but his code was in Lisp. You know, and so 10 times smaller than Lisp is pretty darn good, actually. If it was in C, it would have been way bigger. And by the way, there was a bug in his code, so for what it's worth. So say my students. I actually haven't checked this. Now this month, because the UAI deadline is coming up, the students are running around and implementing a lot of the other popular algorithms, which are small variants in many cases on this. One of them that's kind of fun, actually, requires you to maintain a priority queue of the variants in these messages. And so a distributed priority queue is actually a data structure I haven't seen before that I think we can cook up pretty easily here. Anyway, what are some of the research issues here? Well, there's optimization opportunities at both these layers. So at this layer, which we call the ION, the inference overlay network, you know, we can shape these however we want. Chord is an example of an overlay network. You choose your neighbors, and we can choose our neighbors however we like. And then above that, the actual model that you choose can be tweaked, okay, to make it more efficient to compute. And so we could change the model, we could change the overlay network. What we're really trying to do is get a reasonable approximation for a reasonable cost. So our utility function is how good is our understanding of the distributions for how much messaging we're doing at the physical layer. Okay? And wouldn't it be neat if there was a way to give rules to an optimizer to pick that automatically? And we're not there yet. We're still at the is it plausible phase with this agenda. But this is where we're going with this stuff. So that's research issue number one that we're working on. I probably have time for one more quickly. Another paper that we've been working on recently, which is a lot of fun, is we re-implemented our compiler. We used to have a very simple compiler that really didn't do anything interesting to the programs. And we wanted to be able to try out all sorts of different optimization rules. And we said, gosh, we really need a rule-driven optimizer. And then we looked at ourselves and said, didn't we say that declarative programming was a good idea? And you know, we're not using it. We've implemented our system in C++. Man, are we stupid. So we tried to put our own system in the mirror and say, why aren't you doing what you say you did? And so the name for this right now is declarative in the mirror, which almost spells evita raced. Not quite, but close. So that's the name of our meta compiler. So we represent your program as data, and then we represent our optimizations as overlog programs. And then we represent constraints on which optimizations to run when as a lattice, as a partial order, which is data. Okay, so everything's data. All right? And with just a tiny little bit of bootstrap code, which is a hand-wired, say, MapReduce program, Dataflow program, we have a compiler. Here's our schema for programs. Programs go into that database. All right? There's tables and facts and programs and indexes and stuff like that. That gives you a flavor of it. Why is meta-compilation a good idea? A, because it's a good fit, once again. I'm not going to argue that to you, but there's a lot of things like dynamic programming that are easy to say in Datalog or in extensions of Datalog. And more to the point, you really want an extensible optimizer where you can plug in new compilation rules. And we have a lot of possible platforms we might want to run on. We have P2, which is an internet platform, DSN, which is a SensorNet platform. And then we're asking ourselves, I know this is distributed networking stuff, but really it's data partition parallelism. So shouldn't we be looking at MapReduce? And maybe shouldn't we be looking at this as a language for doing some computations in a many-core environment? And so we want to be able to have our optimizer really consider different optimizations in these different contexts. We also have different applications with different needs. So we want the flexibility. And so that's why we built this meta compiler. The other nice thing about the meta compiler is it's freed us from our runtime, because now that we have a generic compiler that we can move from runtime to runtime, it's not so scary to think about throwing away P2 and writing something for MapReduce, or for that matter, maybe some runtime for a multi-core system. OK, so again, just to prove that it can be done, the classic database dynamic programming algorithm, system-R, is 38 rules in our language. Magic sets rewriting, which is a fancy recursive query optimization, which is, again, sort of the classic in the literature, is more complicated, 68 rules. We pretty much took Jeff Ullman's course notes and translated them into Datalog directly, which is kind of fun, because, of course, they're course notes about Datalog, and we're expressing them in Datalog. It's pretty cool. I'm not going to talk about the runtime, but the runtime has a sort of elegance to it that relates to my work on eddies, if you're familiar with it, on adaptive query processing, and I won't talk about that now. Okay, in my remaining time, I want to try to sort of take this a little bit out of context and put it in the big picture. So what's it to you, right? This whole thing and this sort of odyssey I've been on is about taking my background in databases and applying it to networking. And I think more and more what I'm realizing is that this is not about databases and networking. It's about something much grander and much more wonderful. That's sort of hopefully what's it to you if you don't care about either of those two topics. So it's really kind of about three things. I was trying to put this together in the last couple of days. What are we doing? One is that, in Jim Gray's Turing Award talk, he talks about the dream of automatic programming. And then Butler Lampson in his JCM 50th anniversary article refers to it and then talks about some instances where we kind of have some stuff like SQL and spreadsheets. They're sort of declarative. But for the most part, he's like, that stuff doesn't work that great. And I think actually it does work pretty great. And the thing is, we got to just start looking at some new domains. So we did it for data. I've been doing it for networking for a couple of years. I think you can do a lot of stuff in networking pretty naturally in a declarative language. Let's start knocking off some of these things one thing at a time, OK? So that's one piece of this, is where can we do automatic programming? And to some extent, domain-specific languages are a topic that people are talking about a lot again. And I think taking a very declarative look at those is a very natural thing to do. So that's kind of one piece of the puzzle. A second piece of the puzzle, which is super hot right now, is parallel data flow runtimes. And by this, I mean MapReduce, for example. That's the one that everybody's sort of talking about. But also what the people who do parallel computing, who are now have come back to life after 10 years in a cave, are talking about embarrassing parallelism, right? Well, these programs I've showed you up to now have recursion and aggregation and negation and things that aren't embarrassingly parallel. They're a little bit more than that. They're somewhere between a Turing complete language and simple embarrassingly parallel programs. And so in these environments where we have the ability to do data parallelism and we understand that, are there some sweet spots where some limited languages that are more expressive than the dumb stuff, but less expressive than the Turing complete stuff, have a role? And in that sweet spot, kind of what are the nice languages? What applications do they solve? And this is a conversation I'm really just barely starting with my colleagues. And love people's ideas on that. And then the last piece, which I'm very excited about because I'm a database guy, is I'm interested in applying this stuff to data management and to information on the network. And at the end of the day, I'm most interested in getting the data and making sense of it and moving it around so that you can get answers. And so this idea of getting my friends in machine learning to be able to program actual distributed systems, that's a big hurdle we're in right now. Those people live in the world of MATLAB. Right? They don't even live in the world of C++. Can I give them something that they would actually like reasonably, that I can actually run on Planet Lab or run on a multi-core system? And I think this is doable. I think this is quite doable. And we have some instances. There's MapReduce work here from Andrew Ng's group at Stanford where they show some embarrassingly parallel things you can do. We've been doing some things that involve recursion and negation and so on, so they're a little more complex. How do we get these guys building stuff across distributed systems, I think, is a really valuable and important thing. So these are three of the pieces where I think we have some help to give or some ideas to contribute.
Your language it's very cool. It looks a lot like constraint logic programming over some domain D. Is it, or is it something different?
So it's a logic programming language. It's not constraint logic programming because they tend to have fancier constraints. So we haven't gone the whole way, if you like, of constraint logic programming. But Datalog is a logic programming language. CLP is in that same family. So there's lots of Europeans who know more about this than I.
And in that same community, there's work on soft constraints as well as hard constraints, which lets you say you like something to be satisfied, but you're not going to drop dead if it's not, and trade them off in various ways. You looked at that?
I have not. There's other scary stuff like disjunctive Datalog where you allow multiple hypotheses to coexist. Dan probably knows much more about this than I, so I'll pass this to Dan. I know this stuff is out there, and one of the things I've been trying to do in this project is learn enough of that literature to make progress without falling into the black hole. And you're deeper down the hole than I've gone. It may still be safe there, though, so I may need to go spelunking a little deeper. So I welcome that as input, so I need to look at soft constraints. OK, thanks.
So in the example that you gave, it seemed like you had explicit rules for moving data around, for moving tuples around. And was that just a pragmatic sort of given to the fact that, really, I would have thought that you would have just said you had an automatic data propagation system which kind of declaratively moves things around. Was that is that something which you're planning to address, or is it something which you're...
I'm going to slightly rephrase your question, if that's okay. Stop me if I'm wrong. So the examples I showed had explicit statements about where data must be. It didn't actually have explicit specifications about how to move the data. It just had a specification where the data had to land, right, which is actually already one step better. Right, there's no send in the language. Okay. But why, as a database person, am I explicitly putting layout into the language? And the answer there is we started with you had to have links, and without links, you couldn't have a network protocol at all. So at the bottom of this thing, you need to have specification of neighborhood, of I am your neighbor, and physically I can send you a message at the lowest level. All right? And so some of these protocols, like CORD, what you can do is once you've got CORD implemented, you can do any-to-any routing in CORD by key. And you can hide all that @sign stuff from there on up. So if you're willing to build a point-to-point routing protocol using this lowest level, you can then hide the @signs from there on up. Okay? And at that point, you're free to re-optimize. And in essence, CORD is doing that. Okay? It's allowing the placement of data to change. You have to write that code somewhere. We're doing it in the logic language. Okay? But it is certainly possible and very natural for us, as you say, given our background, to say, oh, you don't want to have to specify where the data is placed. So of the three things we're working on now, the one that I didn't talk about is automatic replacement of data. And automatic replacement of rendezvous points. And that's a kind of fun topic. So thanks for bringing that up. Yeah, it fits, but you have to start at the bones with something.
So is there any notion of efficiency of how you, when you've written things declaratively, there are various, I mean, there are differences in Prolog and in other languages. Different specifications of the same thing can have radically different behaviors when you actually try to run it through the standard engines.
Okay. Good. You said two things there, Prolog and standard engines. And so we have neither of those things. Okay. So Datalog doesn't have an operational semantics the way Prolog does. Prolog has cuts and various other things that actually control execution. And we'd like to believe that, the optimizations under the covers will evolve and change as you go to different environments. And because those optimizations are rule-driven, we should make that easy for people. We'll see. Okay, but to be clear, it's not Prolog in part because it is fully declarative. Well, thanks. This was fun.